Okay guys, so we're going to have a look at the reactions in your Year 13 notes in haloalkanes regarding the haloalkane reacting with sodium hydroxide in particular conditions. The conditions that change really are the solvent that is used. So if you look in your notes, you'll see a reaction of sodium hydroxide with haloalkane. Now, what changes there is the solvent that is used. It can either be aqueous, so water, or it can be an alcohol. So I've just chosen ethanol here. Now the examiner might refer to this solvent as ethanolic or as alcoholic, or maybe even propanol might be used. But either way, you need to pay close attention to which solvent is used, because that will determine the product that you get. So I've just written out the full equations for the reaction of the haloalkane with sodium hydroxide in aqueous, and for the same for ethanolic. I've just written ETH here in brackets for ethanolic. And you notice that with sodium hydroxide in aqueous conditions you get an alcohol, so it's actually a nucleophilic substitution reaction where the halogen atom is replaced by the OH and we get an alcohol in both instances. For the full equation I've used sodium hydroxide here. The examiner may well refer to potassium hydroxide, but you get sodium chloride, sodium bromide, whatever the halide is. And again, there's the ionic equation. You can see sodium isn't in it, so it's a spectator ion. So in other words, briefly, with aqueous hydroxide ions you get substitution and the product is an alcohol. So wherever the halogen is, it's replaced by an OH. When we carry out the same reaction or the same reagent, okay, but we use ethanol as our solvent, we this time get an elimination reaction. An elimination meaning that we actually remove some atoms from the parent molecule, the haloalkane in this instance, and we will get an alkene, ENE, okay. In both instances, and we'll look at how we determine which alkene is made in a minute. We also get the sodium halide if we use sodium hydroxide, and we get a molecule of water. So those are the two ionic equations, and those are the two full equations. So if we just go down here, then we have a look at one nice simple example to get us going. So we've taken let's say a 1-bromobutane here, and we're looking at hydroxide ions in aqueous, so that's again back up to here to the substitution reaction. The X, the halogen, is simply replaced by an OH, and in this case we would get butan 1-ol. Okay, very simple. And then with the hydroxide ions in ethanol we get elimination. Now how do we know where the double bond forms? Well, the halogen, the functional group, will be removed, eliminated, and a hydrogen from an adjacent carbon is also removed. So there's only one adjacent carbon in this instance, which is the one I'm pointing to now, and so the double bond will form there, and you will get one product only. You will get but1-ene. Let's go and look at one that's a little bit more complicated. So I'm not going to do these all for the hydroxide ion in aqueous, because all you're doing there is taking the X off, or the halogen off, and putting the OH group where that X happened to be. It doesn't matter if there's one X or if there's two halogens or three. You take them all off and you replace them just with 1, 2 or 3 OHs. Okay, and you'll get maybe a diol and then also triols. So let's look at again hydroxide ions in ethanol, but this time we have got a halogen which is on position number 2 in a 4-carbon chain. So this time we have to remove, of course, the halogen atom, but we have 2 adjacent carbons. So we can remove this hydrogen and the double bond would form there, or we can remove this hydrogen and the double bond would form there. So of course we're going to get more than one product this time. So if we take this first one, we remove this hydrogen, we will get but1-ene, the double bond forms here. If we replace or remove this hydrogen and the halogen, of course, we get a double bond forming here, okay, which is but2-ene. But there's another little trick here which you need to be careful of, because but2-ene, if you think back to your isomerism earlier in the year, forms E and Z but2-ene. So we have a double bond, of course, with a hydrogen and a CH3. So different groups on this side of the double bond, and a hydrogen and a CH3 here. different groups on that side, so you need to watch out for EZ or cis-trans isomerism there also. Let's go look at the next example. Okay, so we've got let's say it's bromo, 2-bromo, 2-methyl butane. Again, elimination reaction, hydroxide ions in ethanol. And so we can remove this hydrogen, making the double bond form there. Gives us 2-methyl but-1-ene, only one product. Okay, there's a hydrogen there and a hydrogen there. So on this side of the double bond, there are no different groups, same groups, so we won't get EZ. Down here then, if we remove this hydrogen, we will get the double bond there. And that gives us 2-methyl but-2-ene this time, as opposed to 2-methyl but-1. So does this give EZ? Well, let's look at our double bond carbons here and here. This one has got a hydrogen and a CH3, so two different groups. Does the same happen over here? This carbon has got a CH3 and another CH3, so no EZ there. Those two groups are identical. Okay, so hopefully that makes some sense to you. I'm going to look just at another couple of slightly, not more complicated ones, but slightly different ones here, and we'll see how they go. Okay, so if we look this time, we've taken haloalkane, which has got two halogens, one here and one here. So again, we really would do exactly the same. If it's with hydroxide and aqueous, we just take the halogens off, replace them with OHs, and this time we will get pentane 1,5-diol. Don't forget when you have two OH groups that it's a diol, of course, and that the E is present, the vowel here is present in the name. Now, if we have OH in ethanol, so we get elimination, we will get elimination there, so this X and the adjacent hydrogen, the adjacent carbon, and this X and again the adjacent one here, so we get a double bond there, so we will get something with two double bonds in it, and it will be penta 1,4-diene. Again, remember, if we have two double bonds, we've got to put the vowel in after the pent or the prop or the but or whatever it happens to be, and again, two double bonds is a diene. Okay, so that's how you deal with ones there. Now we're going to with two halogen groups in them. So we'll look just at another one. Okay, a little bit different again. So if we look here, okay, same sort of idea in that we've two halogens on a 5-carbon pent on positions 1 and positions 4. So if we look at the OH minus in ethanol, okay, we will remove this, the halogen, and a hydrogen from an adjacent carbon, so that one will go. But over here we have two options. We can remove this halogen, of course, but we can remove this hydrogen, or we could remove this hydrogen. If we remove this hydrogen, okay, the double bond would form there. Of course, the other double bond will always form here. So this time we would get penta, again remember your A, 1,4-diene, so double bond there and double bond there. However, we can also remove this hydrogen from the adjacent carbon, okay, and that would give us a double bond here, and of course we're always getting this one there, and that would this time give us penta 1,3-diene. So in this instance, okay, unlike on that board where we only had one alkene possible product, here now we have two alkenes as possible products. So bear that in mind. Okay guys, you have lots of questions on page 21 of your notes, questions 6 and 7, which will allow you to practice these. Any other queries, you can of course see me. Hope that helps.